Hello and welcome to Lecture 3 for Unit 10, talking about climate and climate change. Today we are talking specifically about how the climate will change. So we're going to try and make this as quick as possible. Some of this is a review from our previous unit about the atmosphere, so I may go a little faster at times. If you need to, pause or go back to a slide to get something you missed, because I want to make this nice and quick. So the first thing we want to talk about is the greenhouse effect. We did talk about this in a previous unit, so I won't go spend too much time on it, but we compare the Earth to a greenhouse because the Earth's atmosphere is like the glass in the greenhouse. And if you know anything about glass, you know the glass lets light in, but it doesn't really let light out, right? So sunlight comes in and warms the Earth. All right, so that energy radiates up from the surface. You guys know, so it kind of comes down, bounces back up. So if you think about the Earth, there's the atmosphere above it. Light comes in, bounces off the Earth, doesn't get back out. Not all of it anyway, some of it does. So this warms up the atmosphere. So this area all in here, this atmosphere is warmer than it should be. Why is that? Because there are extra gases there. Okay, there are gases in the troposphere that used to not be there. Here's a much better drawing. You've seen this before already. I'm not going to spend too much time on it. Here is the sun's rays, and normally more of it escapes out back into the atmosphere, but because we've got extra greenhouse gases like carbon dioxide and others, it's trapping more and more heat in. A definition for a greenhouse gas is a gas that absorbs and re-radiates infrared radiation from the sun. All right, and infrared is a little fancier way of saying heat. So the major greenhouse gases are water vapor, carbon dioxide, methane, and nitrous oxide. Of these, water vapor and carbon dioxide account for most of the absorption that occurs in the atmosphere. We're doing a lab on that very soon. Or actually, we may have already done it. So you'll see exactly how much of each of these gases make up the atmosphere. Now, you might be thinking water vapor. Well, that's just like, that's naturally there, right? It gets evaporated from lakes, from rivers, and it's not a bad thing. But if you remember, water can usually, water can trap heat pretty well. We talked about that when we discussed weather. When an air mass travels over water, that water retains lots of heat, and it usually keeps cities near the coast warmer. And water has that quality. Water can hold on to heat for longer. So, despite all the good things that water does, water vapor in the atmosphere actually kind of works against us and helps warm the planet. 85. So we had a geochemist named Charles Keeling. He'd installed an instrument at the top of a tall tower at Mauna Loa in Hawaii. So it doesn't seem like a big deal, right? But what he wanted to see is how much carbon dioxide was in the air from forests and cities where carbon dioxide levels vary every day. And you're thinking, well, wait, Hawaii, Hawaii is nowhere near the major cities of the United States. It's kind of a really remote area. Surely you wouldn't find much carbon dioxide there, right? Wrong. So we know that from the previous lecture that winds, it blows steadily. Remember those trade winds? So there's the equator, and the trade winds kind of blow that direction right there. That's a terrible arrow. The trade winds blow, right? And the trade winds brought the human activities to Hawaii, right? So they brought the carbon dioxide to the remote island. So at Mauna Loa, the average carbon dioxide levels for the entire Earth could be measured, right? So Mauna Loa is remote, but because the winds circulate all the air on the Earth, he could get a pretty accurate reading on just how much carbon dioxide was there. And what did he find? Much of the carbon dioxide that's released in the air dissolves in the ocean or is used by plants, right? So most of it gets used. Like, we want carbon dioxide, so plants use CO2 in photosynthesis, right? In the summer, growing plants use more carbon dioxide for photosynthesis than they release in respiration, causing CO2 levels to drop. So CO2 always goes down a little in the summer. In the winter, dying grasses and falling leaves decay and release carbon that was stored in them, causing those levels to go back up. So we normally would see this fluctuation of rising and falling, right? So CO2 levels were always sometimes a little higher, sometimes a little lower. But until we started really measuring them consistently all year, all we knew is this rising and falling pattern. All right, so after running the experiment for a few years of measurement in Mauna Loa, it was obvious that the levels were undergoing changes other than seasonal fluctuations. So we couldn't blame the rise of just a really hot summer where the plants grew a lot and or grew less and absorbed less carbon dioxide, right? Each year, we were seeing from 85 on high carbon dioxide levels of winter that were higher and higher each year. And the summer levels did not fall as they used to. So we're kind of getting this higher baseline, right? Since 1958, we reasoned, and we used some ice samples to figure that out. The level of carbon dioxide in the atmosphere has increased over 20%. All right, this is due largely to the burning of fossil fuels. So if you think about what was going on in '58, well, more people were buying cars. It was sort of the heyday of the Ford assembly plant, so cars were becoming more cheaper. They were not just for the rich. Pretty much everyone was getting one. It was part of the American dream, and that led to a burning of a lot of fossil fuels. You can see this beginning in 1958, ending here with the data in 2010, just a steady increase, okay? And this does account for the seasonal changes. If you guys see the top of the little blue marks, this is showing the highest point of the year and the lowest point of the year in the summer, and then that purple line is the average, the middle point between that. So you can see that middle average is going way up, right? So we're starting at parts per million. This is the measurement for used for gases in the atmosphere, 310, ending at around 390 in that period, right? So that's a pretty big increase. It's a pretty big increase over this period. So from 310 to 300, 310 to 390, right? So that's an increase of 80 parts per million, which is a lot. Most scientists think that because greenhouse gases absorb and re-radiate infrared radiation to Earth's surface, more greenhouse gases in the atmosphere result in an increase in global temperature. So this is, becoming more and more certain by scientists that this greenhouse effect is real. A comparison of carbon dioxide in the atmosphere of average global temperatures for the past 400,000 years supports this view. All right, so what scientists have been able to do is, so in places like Antarctica, where there's ice that's been frozen and glaciers for a couple million years, we've been able to dig down into the ice, and we can kind of measure those carbon dioxide levels, right? So we expect to see less carbon dioxide here in earlier years and getting more and more and more. But what we can do is we can go back and compare those 400,000 years and see a major increase. Okay, so today we're releasing more carbon dioxide than any other greenhouse gas in the atmosphere. Millions of tons of carbon dioxide are released into the atmosphere each year from power plants that burn coal and cars that burn gasoline. Millions of trees are being burned in tropical rainforests to clear the land for farming, right? So not only does farming itself, the actual act of farming, release greenhouse gases in the atmosphere, but think about it. If we're cutting the trees down, what do? Trees remove carbon dioxide. So those natural filters we have in the form of trees and plants, or if we're cutting those down to make way for more methane and carbon dioxide producing farms, we're kind of shooting ourselves in the foot twice there, because less trees is a bad thing in terms of reducing CO2. So the amount of greenhouse gases, including carbon dioxide, methane, and nitrous oxide in the atmosphere, is increasing. Just the overall tonnage, right? We're putting more in than we ever have at any other rate in history. All right, so here are the major greenhouse gases and where they come from. We've already kind of gone over much of this. Methane, animal waste, right? So obviously, cow poop, things like that. When you burn biomass, like burning campfires, or when you burn peat, or when you burn any kind of living things, that's biomass. Fossil fuels also release some methane, and nitrous oxide comes mostly from burning of fossil fuels and fertilizers. And water vapor, we know, comes from natural processes like evaporation. So these are the big four here, greenhouse gases. And of all of them, this is the one that kind of gets in the crosshairs the most. We're going to see from Steven Schneider about his views on what we need to do to reduce that, some of his strategies for reducing that CO2, and we'll have a nice discussion about that in class. So, global warming, here's a definition for it. I don't think we've seen that yet. We've seen climate change, we've seen greenhouse effect, but this is a definition for global warming. It's a gradual increase in the average global temperature. Pretty easy, right? So because this increase correlates to an increase in greenhouse gases in the atmosphere, most scientists conclude that the increase in greenhouse gases and other factors have caused the increase in temperature. Pretty obvious, right? If you, sit in a hot car and don't roll the windows down, it gets warmer and warmer, right? If you roll the windows down, you let that heat out. What we're doing is we're just trapping in more and more heat. Scientists are pretty smart guys. I mean, they see data showing, here's one graph showing, hey, there's an increase in CO2, right? And there's another graph over the same time period showing a similar increase in temperature. You kind of put two and two together there, and you could say that the CO2 has something to do with the average temperature. Earth's average global temperatures increased during the 20th century, and many scientists predict that this warming trend will continue. We're only adding more people, right? Thousands of experiments and computer models support this hypothesis. So we're seeing the second full decade now of real data, real modeling, real science that's supporting this. So it's becoming less and less of a hypothesis and more of a bankable prediction. And here you can see from 1895 to 2005, this is average surface temperatures. So I think a student recently mentioned he'd like to know what the actual median temperature is of the Earth, and you could use this data to figure this out. There are cooler periods here, right? So you can see here in 1910 or so, it was cooler. It gets warmer, cooler, warmer. But look at the overall average, and this number here, this line is kind of there to give you an idea of that. So if you're looking at the y-axis, it says the difference from the 20th from 20th century average temperature. So this is a difference from the average. All right, and you can see sometimes it's a little cooler, sometimes it's a little warmer, but notice the higher average just gets higher and higher. Goes back down in 1945, goes back down in 1955, but we got to think long term here. Remember the difference between weather and climate? Climate's a long-term picture, and just look since 1965 even, just the average climb in this range right in here, the one we kind of looked at before when Mauna Loa was when that scientist was measuring the carbon dioxide at Mauna Loa. You can really see that it's just steadily been increasing, especially in the last 30-40 years. So as you saw in that last graph here, temperatures are not necessarily rising at a constant rate, right? We have a rise one year, maybe a slight fall, then a rise, or rising in all parts of the world, right? So we might see, Rochester have lower average temperatures over a period and another city having it. So we can't think like that. We have to think globally. As the temperatures and carbon dioxide levels, short-term variations in temperature are superimposed on larger trends, such as patterns of precipitation, frequency of fires, and extreme weather events. So we can't just look at temperatures, because temperatures bring with it other things, right? The extreme weather events are, some of these things are increased hurricanes, All right, we're seeing more powerful hurricanes more often. Hurricane Sandy was an example of a hurricane that made its way more north than normal. We're positing that the waters are warmer. We're seeing, what's going on in Australia. Think about that, you guys. These frequency of Australia. That says Australia. Trust me. Let me actually go back and delete that. I'm such a perfectionist. Australia, California, we're just kind of forgetting about it, but California was devastated by wildfires in 2019 and parts of 2018. And we're seeing, in 2018 in Rochester, the record, the wettest spring in the history of Rochester, New York, right? And that increased the lake levels, and we've seen flooding along Lake Ontario. So most scientists use global climate change rather than global warming, right? Because it's not just warming. Climate change is a little bit more of an accurate, more broad description, right? So global warming is part of climate change, but climate change itself is a little bit of a better description. Okay, so we're going to talk more about the effects of climate change in the next lecture. But a lot of these projections and predictions are based on computer models. All right, so scientists use mathematical relationships among drivers. So these are sort of the things that move along temperature increases, like solar input, that's the amount of sunlight, wind patterns, cloud cover, and response variables such as troposphere temperature, surface temperatures, ice covers, and sea levels. These relationships are expressed as equations and complex models, right? So all the information that weather satellites, weather balloons, even ground-based weather stations, all that data gets put into computer models that kind of project out what a year will be like in terms of temperature, how much precipitation it will get. And these models are all consistently saying and backing up the idea of climate change. All right. They use these models then to predict how factors like temperature will be affected by certain variables. So scientists validate the models by starting with historical conditions and then comparing model projections to known, to known changes in climate. The models are constantly being updated with new information. About a dozen different models similarly predict widely increasing temperatures that are not simply driven by natural or solar variability. And it says here, humans are playing some role in climate change. I think that is even being a little conservative. Like if you think about the graph that shows CO2, carbon dioxide does naturally occur in our atmosphere. It's always been there. It's a product of respiration. It's a product of our natural carbon cycle. But it has not increased at the speed that it has been throughout history. And I think to say that that may be because of people, is it kind of ignoring some science there. It most positively is. So hopefully you learned a little bit about climate change, about how maybe you want to call it global climate change instead of global warming, and maybe you learned a little bit about over time, the last 30, 40 years, even 100 years, how this pattern has changed. And it all kind of ties back to where did the CO2 come from, right? We're burning more fossil fuels, we're building more cars, more factories, more people. We're expanding as a society, which is a good thing. But with that may be coming in these consequences. So please get ready for a short quiz. And hopefully this is kind of feeding the fire for our little debate and our discussion we're going to have pretty soon about the overall argumentative essay topic. Hope you guys have a great night. Take care. This is Mr. Orr signing off. Go Bills.